So everybody has seen like all the AI art on like Facebook and stuff, and grandma's commenting on it. But basically, this video is just a really brief overview on how they work on the inside. Um, Obviously, one of the leading models, Stable Diffusion, is a type of generative AI model that can create realistic images from noise, pretty much. Alright, let's just do like a brief overview on the inference process. Alright, at the core of every single AI model out there, you have to convert text into tokens. Text is continuous, yet tokens are discrete, meaning it's easier to generate or condition stuff based off of tokens. As you can see here, it turns a cat eating a burger into 5 separate tokens. Then this gets put into a model called clip and gets turned into embeddings. And then during the denoising process of the actual model, it turns noise into actually a coherent image. As you can see here, step 1 starts off as noise, then it slowly yet surely turns into the cat. The thing is about these models, they can take some time to generate, but now they've been getting faster and faster because we figured out how to optimize them better. So what exactly is CLIP? Well, CLIP stands for Contrastive Learning Image Pre-training. It's a model developed by OpenAI, yes, the people behind ChatGPT, that can understand images and text and connects them together. So how does it work? CLIP is trained on a huge dataset of images and their captions from the internet. It learns to match images with the right text descriptions and vice versa. For example, if you show CLIP a picture of a dog and the words "a photo of a dog," it learns that these go together. But why is CLIP so important for Stable Diffusion, you might ask? Well, it acts as a bridge. Basically, you type in, for example, a cat riding a skateboard, and CLIP helps the model understand what that means, so it can generate an image that matches your description. It's pretty cool, honestly. But why diffusion over autoregressive models, you may ask? Well, because diffusion generally is easier to train than autoregressive models because, for example, with a transformer, you don't have to deal with this horrendous memory scaling, and you get highly good images, obviously, because noise acts as a compression method, pretty much. All neural networks, as we know it, are advanced compression models, pretty much. But basically, both are very fast in their own ways. So how do you train these diffusion neural networks? So, to make a data set, you obviously get a huge amount of images, and then you progressively noise them, like apply noise to them. And then you train the neural network to denoise it. And that's the whole core of diffusion. That's it. You can go fast, you can go slow. You may be also thinking though, but sure, the larger the image, isn't it more expensive to train? Well, yes. And that's why most of these diffusion models actually employ something called a vector quantized variational autoencoder. I know it's a mouthful. But basically what it does, it takes in an actual image, turns it into a set of vectors, basically numbers, and then it converts those numbers back into an image. This is good because it's smaller. You can turn 1,000,000 pixels into 500 vectors and then back. This makes it easier to train and keeps detail, obviously. It's awesome. Here's a different thing to consider. How do they know? How do these models know? So basically, in the embedding space of each model, they cluster up. And when they cluster up, you can actually predict the gradients and think of it as dropping a ball on a mountain. It'll want to settle down to the bottom. So it slowly yet surely drifts over to the spot, and then boom, it's the image. This is stuff you probably already know, so I'll just show the code and explain what happens within the model itself, and then you'll probably get a better understanding of it than this video will ever tell you, because honestly, nobody knows what they're talking about. We just know roughly what it does, not exactly what happens within. So all approximations. So at the very start of the inference pipeline, you obviously have to define your generate function. But here we find something interesting. The latence width and latence height is 64 by 64. So the model is actually only generating 64 by 64. You have to load clip weights in, and this is where we find some interesting things. For example, clip's embedding size is actually 768. And that's fun to know, which will be important later. Right, so here's the autoencoder afterwards. It gets loaded into memory too. Basically, it takes a 512 by 512 image and turns it into a 64 by 8 list of vectors. That means each vector is 8 long. So it could be 1, 2, 3, 4, 5, 6, 7, 8 within. So basically what it does is just transposes it really small and then expands it back. So it's more efficient for the model to actually compute it. Decoder is basically the same thing, just inverted. 8 by 8 to 512 by 512. That's it. So the thing about Stable Diffusion's UNet is that it is massive. So I'll just outline what happens within it, not exactly what happens inside it, because it's nothing too special. It's just some residual blocks and some attention blocks, which I'll obviously cover later, but it's not important to look through the whole thing. Just a rough understanding is already good enough by itself. At the very start of Stable Diffusion's inference process, at the very first step, before anything even happens, you pass your input into clip. Now the thing is, clip is limited to 77 tokens. But basically, within clip's code, it embeds the tokens, right? Using the clip embedding class. And then for each layer within clip, it updates the embedding. And within each layer norm occurs, which is very expensive in computation, and attention, self-attention. There's this researcher called HeFed, and he made a really, really, really good blog post about multi-head attention, much better than I'll be ever able to explain it, honestly. But basically, self-attention is a neural network's way of weighing how important a token is in a sequence. So basically, it's... How important is this word? But if you're this far through the video, you already probably know what that is. So then, at the very end of this process, clip outputs an embedding. You know, the one that matches with the image. So then we move on to the next step of the inference process, which is generating random latents and the time embedding. Now, honestly, I don't know what the time embedding does. This function is just so mysterious looking to me. Still in high school, I don't know what the hell's happening here. So I'm gonna talk through this, okay? So what happens here is that we create a list of 160 numbers that get smaller and smaller, right? These numbers are used as different frequencies, as you could call them, for our embedding. Then we multiply our time step by each of those frequencies. This gives us a new list of 160 numbers, each one showing how the time step interacts with a different frequency. Then we take the cosine and sine of each number in our list, then stack them together into one big vector. This gives us a unique fingerprint for our time step that a neural network can use. Basically, it helps neural networks understand where they are in a sequence. Like what step they're on in a process, you know? Like the diffusion steps. So, at the very, very start of inference, you have to compute something called the time embedding, which we just covered. Then we normalize everything in terms of the embeddings, like time embeddings. And then we go on to the UNet. And then from the UNet, we get an output, the latents. Then we pass that over to DDPM, which I'll cover next. Now, the DDPM sampler is a beast. So, what it does, right, is that it takes in the current time step, the current noisy latents, and the model's output. Its job is to compute the latents for the previous time step. Pretty much denoise. So in step 1, we store the current time step as t and calculate the previous time step as previous t. This is because in diffusion we go from t to t minus 1 each step. Because when you train it, it's t plus 1. In step 2, we fetch the cumulative product of alphas, the noise schedule, for the current and previous time steps. Alpha prod t and alpha prod t previous are to track how much signal remains at each step. Beta prod T and beta prod T previous are the complementary noise amounts. Current alpha and current beta T are the ratios for the specific step. And then for step 3, we estimate the original clean image, x_0, from the current noisy latence and the miles predicted noise. This is obviously a key step. It undoes the noise. It undoes it all, and that's what the model is. It's a denoiser practically. And then we calculate the coefficients, one for the predicted noisy sample and one for the current noisy sample. These coefficients determine how much each component contributes to their next step. And then we combine the two components, the denoised prediction and the current noisy latence, to get the mean of distribution for the time step. This is the best guess, for what the latence looked like a step earlier. And then if we're not at the very last step, if t isn't 0, we add some random noise back in, scaled by the correct variance for the step. And then if it is the last step in the whole process, we pass it through the decoder, the autoencoder's decoder, and then we rescale the pixel values from 0 to 555, in that range. And then we convert the tensor to a NumPy array and return it. That's it. If you probably watched this, I don't know, I might have been wrong for some parts, but this is just like the best I could do. Alright, I might do a video on Transformers next or something, I'm not sure. Maybe even Swarmformer, that might be an interesting one. Please, if you have any questions, ask them in the comments or something.